Hello, my name is Ahmed Barakat, and this is my analysis to Lab 1 of Physics 2211. To get started, the main objective of the experiment was to observe an object moving at a constant velocity and compare the experimental values with the computational model. In this case, we have a code that takes in the initial conditions of the motion of the object and predicts the expected outputs of the experiment. And it is important to note that in this experiment, we assume that the net force is equal to 0 and there is no air resistance or friction acting on the object. It is also important to understand the main physics principles involved in this experiment. The experiment revolves around Newton's laws of motion, the first one being the law of inertia, and here we have a demo of what this means. It states that an object in motion will remain in motion, and an object in rest will remain at rest unless acted upon by an unbalanced force. Additionally, Newton's second law states that an object is in constant velocity if the sum of the forces F net acting on the object is 0, and as the momentum principle states, when the net force is 0, the momentum will continue constantly, and as a result, the object will continue moving at a constant velocity. Okay, so here are some of the formulas we will be using. The velocity and the position update formulas are really important since we will need to use them in GlowScript as shown here. Moving on to tracker, but first of all, it's very important to identify our system and the surroundings. The system is what we see circled here, and everything else will be considered the surroundings. So I use tracker to set the axis of the object's motion, and I use the motion tracker to plot the position versus time graph. I set the initial position of the object at the origin, and then I use the data from tracker to calculate the average velocity of the object, for which I use the change in the position over time for the first frame of the video, and this velocity is what I use in GlowScript since we know the velocity will be constant. So this is the first section of code for the system and initial conditions. I modified the first section and included the mass of the object, which is in kilograms, the SI unit for mass. Then I used tracker data and put the initial position and calculated the velocity as shown in the next slide. Okay, so here are the values I used from tracker, the initial and the final time. They also used the initial and final position. And then I used the average velocity formula and used the position vector on the x direction since the other axis will not change, and I got minus 0.65, and the negative here proves that my object was moving to the left. And then I used the initial time from tracker and adjusted delta t, which is the size of each time step between each frame in the tracker of my video. Okay, so moving on to the next section of code, which contained the while loop of motion prediction. First, I inputted the final stopping time of the video used in tracker, which was about 0.8 seconds. And then I left the Fnet vector unchanged since the net force in our experiment is assumed to be 0, following Newton's first law. Since we know Fnet is equal to 0, if we inputted 0 here, this whole term will cancel out, leaving us with Vf is equal to Vi. Therefore, as the while loop is running, the velocity is remaining constant, knowing Fnet is equal to 0, and the position vector ball.pos will change with each time step where the loop repeats. After I ran my code in GlowScript, I was able to compute a position time graph in a Google spreadsheet that compares the experimental and the computational data. Here, I also adjusted the experimental data to be represented as points to make it easier to distinguish between the two. We can see that the observed velocity from tracker is shown to decrease relative to the computational data that appears to remain constant. The position of the model data is changing at a constant rate because remember Fnet was equal to 0 when we set up our code, meaning Fnet was always equal to Vi. However, in the experimental data, this is not the case. This is due to an Fnet acting on the object, causing it to decelerate with time. Since we know in real-life situations, we have other forces such as frictions and their resistance acting on our object. Moving on to the what-if questions. To answer the first question, The answer is that the magnitude of our velocity vector wouldn't change. However, the direction will be to the right instead of being to the left, since flipping the axes will only change the direction. And to answer the second question, while it is possible to know the forces acting on the object, we can't precisely measure those pushes and pulls in our experiment, which is why we set the net force equal to 0 in our calculations and code in GlowScript. Before we end, it is also important to mention possible sources of error in our experiment, including the friction and the uneven surface of that object was rolled on. Thank you for listening, and I hope this was informative.